All right. Hello, everyone. Welcome to another edition of Blockchain Speaker Series at UC Davis. And so today it's very exciting to have Preston and Loon from Prysmatic Lab. And this is a talk that we've all been waiting for. All the previous speaker, anytime we talked about Ethereum 2.0, Serenity, proof of stake, they all seen the schedule. They all said, okay, Preston is going to take care of it. And so he's also a co-founder of Prysmatic Lab, now into the new generation of blockchains and all the exciting stuff around Ethereum and especially Ethereum 2.0. So thank you so much for joining us today. And so with that, please take it away.
All right, thanks for that intro. Yeah, I'm Preston Van Loon, co-founder of Prysmatic Labs, career software engineer, and we've been working together as a team for about almost 3 years now. So introducing you to the team, Prysmatic Labs is 9 people at the moment, and we all assembled organically online. We're not part of the Ethereum Foundation directly, but just a group of really interested individuals, some very smart people in this group who've come together and said, we want to help scale Ethereum and we want to make it happen. And through the Ethereum grants team and through open source grant initiatives, we've been able to fund this project and really get it going. So let's dive into it. Let's start with a very basic, high level of what is Ethereum. I know you guys have probably been talking about it a lot over the semester already, but let's just dive into the important things you need to know about Ethereum today. Ethereum is a decentralized world computer, or at least that's the goal or the vision. It's a blockchain that's been around since 2015 or 2013, somewhere around there. I don't recall exactly.
So Ethereum is a decentralized world computer. At least that's the goal. It's an open source blockchain, been around for approximately 5 years, originally created by Vitalik Buterin and built by a whole group of people all over the world. The network itself, it's consisting of thousands of nodes operating in unison to assemble this world computer consisting of a decentralized global virtual machine. With this type of system, you can build all types of applications, specifically some that are not possible in any other paradigm. For example, decentralized autonomous organization. Being able to launch your own tokens very easily is helpful. And then, of course, you have just generalized decentralized applications. Whoops. So taking a look at the system at a high level, there's quite a lot of things going on. We're not going to dive too deep into any particular part here, except for the proof of work. So if you guys are not familiar with proof of work yet, it's the mechanism by which the block producers in Ethereum are able to, it's the Sybil resistance mechanism, so that it requires a lot of effort to create a block, so not everyone can do it. But in exchange for this service to the network and for securing it, you're rewarded with block rewards. Now, proof of work is basically running a hash function on the inputs of a block repeatedly until you get a partial hash collision that satisfies some level of difficulty. So let's imagine if this proof of work function returned a string of random numbers and letters, and we want a string that starts with 10 zeros, and leaves a 32 length string. If it has at least 10 zeros, then we know we solved the problem. We can submit that input and random number to the blockchain, and everyone can verify it once. So it's a quick way to, well, it's not quick, but it's a reasonably secure way to advance the network. Taking a look at a block and how things fit into blocks, really the important thing you need to know is the block is created with the information about the resulting state after executing this block, after executing all the transactions, which are also included in the block. It includes the transaction receipts and a bunch of metadata that's not as important for what we're talking about. It also includes a reference to the previous block, and that's important. Otherwise, it wouldn't be a blockchain. So what does it mean to scale? It doesn't have anything to do with the scale or a loaf of bread that has a dog face on it, but it means looking at transaction throughput. So let's take a look at a few examples of transaction throughputs through popular payment processors. We have Bitcoin, which can operate on about 7 transactions per second. Ethereum can do 27 transactions per second, and Visa can do a super huge number that kind of blows these two things out of the water. And if these, technologies are meant to displace these centralized payment processors, they have a long way to go, especially since these values I'm presenting to you are at the theoretical maximum. In actuality, it's even lower. So for Bitcoin, they're doing about 3 transactions per second. Ethereum can do 12. And the key here is that transactions on Ethereum are sized differently. So the 27 is based on just simple balance transfers. But if you're interacting with dApps or any kind of contract, then you're going to have more data. So you can't fit as many transactions per block. And Visa reports from a report 5 years ago or so that they're doing around 1,600 transactions per second on average. We don't really know what they're doing because it's all internal, but it's a good estimate that if these technologies are meant to displace Visa, they have a long way to go. Even like 100 times scaling would not exceed what Visa can do or does do. Taking a look at block times, this is something else important. A block time is the average minimum time you need to get your transaction included. For Bitcoin, that's every 10 minutes a block comes along. For Ethereum, it's about 14 seconds. And for Visa, I couldn't really find any reliable information, but think about the next time you swipe your card at the terminal at the grocery store or whatever. It's about 3 to 4 seconds. So if we're looking for protocol level scaling in terms of block time and how long the user has to wait for their transaction to be included, these numbers are not great. You can't stand at the register for 10 minutes waiting for a Bitcoin block to be mined, and even 14 seconds is too long. So that's another point of scaling. Talking about how transactions fit into blocks, because this is all what the blockchain is all about. Typically, a miner is going to choose, or a block producer is going to choose the highest paying transactions. That is, each transaction has a fee associated with it. That miner or block producer collects the fee as reward for including it into a block. And this is incentive for miners or block producers not to just mine empty blocks, because they could potentially earn even more if they included transactions. And the cool thing about Ethereum is that you can fit as many transactions in a block as the gas limit of the block will allow. For example, here on the right, there's an old block from last year that had 74 transactions in it, each with different levels of gas usage. And just a reminder, if you didn't already, gas is the unit of payment or unit of computation cost for running something on Ethereum. The minimum gas cost is 21,000 to do anything, and then from there, each operation in the EVM, each opcode you execute, it costs a little bit of gas, which then you pay in ETH. Yep, and so miners have the ability to vote on this and change it. They can only change it incrementally by a small amount, and they don't typically do this unless that there's sort of a community agreement that 8 million gas limit is too low, so let's raise it to 10 million, and then the miners can coordinate together and vote on that, raise the gas limit. looking at that in history, it's happened quite a few times. This slide is from 2018, and just in this time, you can see these huge cliff drop-offs where the mining community itself has decided to increase or decrease the total gas limit per block. And at the time of the screenshot, it was around 8 million. So how do we scale exactly? How do we go fast on a blockchain? The important part to consider is that to have a great blockchain, you need to satisfy all three corners of this blockchain trilemma. So you want it to be secure, you want it to be decentralized, and you want it to be fast. And trying to figure out how to increase the scalability and how to go faster without diminishing either of the two properties is tricky. So let's dive into a few examples. One idea is, let's just increase the gas limit by a large amount. Earlier, I showed you that block that had 74 transactions because it only had 8 million gas. But what if we made it like 80 million gas? I mean, that's a 10 times improvement. But of course, bigger blocks are going to require more computational resources just to process that block. This is not particularly focused on miners, but for everyone in the network has to process every block to verify it. So you're requiring that full nodes or operators that are running on the Ethereum network or listening need better hardware now than they did before. They need more resources. That increases the barrier to entry for a participant on the Ethereum network, and therefore makes it less decentralized. Where now we'll be moving only towards users who can afford more expensive hardware. So it sounded like a good idea, but we can see here that it takes away a piece of that trilemma that we don't really want to sacrifice. So another idea is, let's just make blocks come around a lot faster. Bitcoin's was 10 minutes, Ethereum is 14 seconds. What if we made it 1 second? I mean, that's a 14 times improvement on throughput. But blocks take time to propagate through the network. And if that block can't propagate through the whole network in that 1 second, you might see another block producer mining a competing block at the same time, but not building on that other blocks. So you end up having these forking conditions. So it ends up increasing the entropy of the system, and not in a good way. It just makes it harder to be a participant, harder to listen, harder to operate. More forks make the blockchain more vulnerable to attacks. It can make it so that no one can really catch up to the head of the chain, or people are confused about what's actually going on. Longer delays in block confirmations for exchanges. In general, it's less secure. So this gives up another piece of that triangle. And looking at it again, it's super important. I saw in your syllabus, you guys have a whole lesson to this, so that's going to be great. It is one of the things we're always thinking about when scaling a blockchain. So with all that in mind, there are two types of scaling. So on the left, we have on-chain scaling, or scaling at the protocol layer. This is preferred simply because everything runs on the protocol layer, even layer 2. However, in the instance of Ethereum in particular, this is difficult to implement because we already have this blockchain that's operating and running. So you're kind of trying to change out the engine on a Formula One car while it's still racing, which is something that's really difficult to do. If done correctly, this can satisfy the trilemma. You're able to design the protocol correctly, you can have a more scalable system without giving up any security or decentralization. It also benefits layer 2 in the sense that layer 2 is a layer of abstraction on top of layer 1, meaning that anything you're doing off-chain still needs to be committed to the protocol itself, to the on-chain protocol. Now looking at the off-chain stuff, you are basically getting throughput by reducing the number of operations that are done on chain. You're able to implement this pretty easily and independently of the core protocol. You can also build these types of scaling solutions specific for your needs. So you can imagine maybe you have a decentralized exchange and you want to run like your own kind of like Lightning network or whatever, where you're able to facilitate trades really quickly on decentralized way, but you still have this operator that will then batch or commit all of those transactions back to the layer one chain. And as a participant, you can, exit that layer two and get your balance back and go somewhere else if you wanted to. But typically it's not as secure or decentralized. Typically requires a trusted operator to run it. So I mean, it's not like a risk of you're losing your funds, but a risk that at any moment it might stop working and then you have to exit, or you could be censored or whatever. So it's not a perfect solution, but it does work for a lot of specific scenarios. So it can be a great scaling solution. All right, let's dive into ETH 2.0. From the words of the creator of Ethereum, Vitalik Buterin, he says that Ethereum 2.0 is a big multi-year long upgrade to massively increase the blockchain scalability with sharding, increase security through proof of stake, and improve some programmatic technical things that didn't go so well when they first designed it. In short, it's a massive overhaul of everything from the ground up. And since it's so big, we are doing it in multiple phases. And being programmers or developers, we're starting our counting at the number 0. And this happens to be the beacon chain. The beacon chain is arguably the biggest piece of ETH2. It's everything to do with proof of stake and the core system. So it has a lot of responsibilities. The beacon chain manages the validator registry. So it manages the balances, rewards, exits of all the validators. You need to have 32 ETH to join. And this is done through a deposit contract on ETH1. So when you wanted to become a validator, you'll send your transaction with some metadata and with that value of 32 ETH, and then you're initiated into the registry. And the beacon chain is responsible for keeping track of that data, of who's in the registry, who's not, who's exited, and things like that. Now, being a participant in phase 0 or in the beacon chain as a validator, you're rewarded with ETH. So every epoch, and an epoch is every 6.5 minutes or so, the beacon chain processes all the information and it looks at who participated in that epoch and who didn't. If you did participate, you're rewarded a small amount. If you didn't participate because you were offline or whatever, then you're penalized a small amount, usually equal to the amount you would have been rewarded. The beacon chain also deals with validator slashing. Slashing is a big part of proof of stake. It's a way to incentivize validators to behave appropriately. As a validator, you join with this stake or this collateral, or like a bond, if you will. And with that, you say, I promise to behave and not act in a malicious manner, or trying to confuse the blockchain or cause chaos or anything like that, which is a very intentional act. And if I do that as a validator, my balance will be burned. Part of it will be burned. I will be kicked out of the system, and someone else can come in and, well, the whistleblower for that can earn the reward. So that's kind of the mechanism to keep everyone working. The beacon chain also deals with shuffling. It's our source of entropy. It's shuffling around validators is calculated every epoch, so you can't know when you're going to be producing blocks tomorrow or in a week or in a month. And the point of that is to diminish a potential attack where validators can collude. Let's say, oh, if you're going to be, I know that you're going to be validating at this point in time. Let's work together to produce this certain state. Well, having a consistent randomness model and then shuffling the validators every epoch makes it impossible to know more than 12, 13 minutes ahead what you're going to be doing. Finally, the important part of the beacon chain is to have finalization. One of the weaknesses of ETH1 is that it has a model where basically the longest chain wins, and same thing in Bitcoin. So if you're able to mine a fork, mine on a fork branch faster than the other chain to which it becomes longer than that one, then it's a reorg event, a reorganization, and everyone switches to the longer chain, and basically all the history of the other chain has been erased from the blockchain because it's been orphaned. This is called a 51% attack when you control 51% of the network. And it means that in ETH1, your transactions are only probabilistically final. They're not truly final, by which I mean, if I had a supercomputer of some kind and I could go all the way back to the Genesis block and mine 10 million blocks faster than anyone else, and we exceed the blockchain, I could essentially erase all history of Ethereum. Not to say that anyone would do that because it would be super expensive, but it's a possibility. Proof of stake has finalization rules where it says once all of the validators have voted enough on this particular state, it's 2/3 of people have voted on it, and done so in 3 epochs in a row, then it becomes final. It means no one, by the rules of the protocol, can build on an older finalized block. So it eliminates that possibility of a long reorg, potentially erasing history. The mechanism for proof of stake, we use something called Casper, which has the friendly Finality gadget. What you need to know about it is that validators have their balance at stake. That's the bond I was telling you about, where it holds people accountable.
Preston, I'm not sure if you can.
It's much more energy efficient than proof of work by comparison. And it has these finalized checkpoints. Another thing that's important here is that to be a block producer in this proof of stake model has a much lower barrier to entry than proof of work. To mine a block in proof of work, you need an insane amount of computing power, usually on the scale of an entire data center worth, or warehouses of ASIC or specific hardware to do that, which can cost a lot of money. Here you need a simple 32 ETH fixed cost to be a block producer. That's good for decentralization. Now, looking at how to become a validator in phase 0, you send your 32 ETH. The validators are watching and observing these deposits, and then every, I think it's 1,024 blocks, or slots rather, they vote on the deposits from the recent voting period, and by that manner we can still reduce the risk of forking in ETH1 with regards to balances. And then once we've come to consensus on what the ETH1 state looks like, we can then wait for the next finalized epoch. Then we have a rate limiting mechanism, so there's not a lot of surging with validators. It goes into a queue. Then when it's your turn to the queue, then you become activated. The minimum amount of time is just over 2 hours. That's the time how long a voting period lasts, plus a finalized epoch. And then assuming there's nobody in the queue, you'll be activated right away. Taking a look at some of the responsibilities of the validator, you basically have two roles. You're either going to be a block producer, someone selected to package and create a block. This is very infrequent on an individual basis because there are only so many blocks per day or per week, and there may be millions of validators. So it's pretty rare that you're going to be selected to propose a block, but in the event that you are, you actually receive a slightly higher reward than simply voting on the chain. So voting on the chain is the role of the attester. Everyone's going to vote. Every validator is going to vote. Every epoch, and you're selected for a random slot in that epoch. And basically, you're saying, "This is what I think the head of the chain should be," and you broadcast your vote. All these votes are collected and aggregated, and if there's a branch with enough votes or enough weight on it that such that 2/3 of validators agree, that can become finalized. Attesters are broken up into committees, which are just really just a subset of validators. In the event that you are selected as a proposer, this is what you have to do. You're going to package a block, which consists of some metadata at the top, so like the slot number, a reference to the previous block, and then a resulting state. Then you have your signature all over everything. You also have your Randall reveal, which is your commit and reveal scheme for the randomness of ETH2 in phase 0. You have your ETH1 data vote, what you think is going on in ETH1, and then you have all the operations. So if there's any slashing that you're aware of from a whistleblower, you can include that. You include as many attestations as you can, because just like in ETH1, block producers are rewarded based on the objects they include into their blocks. So instead of transactions in phase 0, we just have attestations in blocks. Then you have deposits, people voluntarily exiting, and then transfers in phase 1. They're not enabled in phase 0, but there is a space for them in the block. So you package this up, sign it, broadcast to the whole network, and the chain advances. Block processing, so when that block is received by other nodes, they take the pre-state or the state that from the parent block, that's this referencing. You verify the metadata in the block header. You verify that the Randall has been produced appropriately, that it's mixing the previous values. Then you process the data from ETH1, whether or not we've reached the consensus on that data or not. Then you process all the transactional objects, so slashings, attestations, deposits, and such. Then you end up with a post state, which should have the same root, by that I mean hash tree root, as was identified in the block. And if all that goes well, you verify the block, and you know that now you can build on that if you think that's still the head of the chain. Sometimes you'll get a block that's already orphaned and no one will vote on, but you still process it anyway because you're not sure. Attesting, so this is what everyone's going to be doing most of the time. The metadata here is all about Casper votes. So you're looking at what you think the target epoch is, so what was last justified, and then the source, which is what you think of as the head of the chain. Then you have data on the block root, and then in future phases you have cross-linking, so that would be metadata about linking two chains together or data from two chains. Then you also, since attestations are so common or ideally common in nature, so if the network is operating very efficiently, then everyone's sort of producing the same votes. And instead of having all these identical attestations, we can actually aggregate these and into one, and including aggregating their signatures. So instead of having 100 identical attestations, we can have one and verify that it was signed by all 100 of those validators. So that's pretty neat. Basically, package up attestation, broadcast to the network. Everyone's going to consider this for justification and finalization. Taking a look at the rewards penalties, proposing a block yields a slightly higher reward, as I said. Rewards are calculated every epoch. And an important part of Casper and proof of stake is that it's important that we consistently have finality. Finality means that systems operating in a healthy state. We consistently have 2/3 or more validators in agreement. But if we don't, the system wants to fix that as quickly as possible. So the penalties for not participating start to increase, and they increase exponentially as time goes on. So if a large part of the network is offline, they're going to start getting penalized heavy until they get back online. And looking at this table on the right, we're going to start with about 500,000 ETH to kick off the system. Or sorry, it's 2 million ETH to kick off the system. And looking at the issuance rate, for the network in general, it's somewhere between 0.3 and 0.17% for the total network. But on a personal level, you're looking at somewhere between 18% and 10%. And as more participants get into the system, the individual reward starts to diminish. And this just kind of, is an incentive for early adopters. The APR or interest rate or the earning rate that you get as a validator is higher if you join earlier, participate earlier. But of course, there's a higher lockup period and higher risk with that. All right, taking a look at the next part of the phased rollout, phase 1. This is when we actually introduce the data layer, actually bring in the sharding part of E2. In phase 0, where it's kind of like a bootstrapping stage where it's just the proof of stake system. It's kind of like an incentivized testnet because all you're really doing is agreeing on the state itself, not really doing much with it. Well, here in a shard chain, you can add data to that piece. And this is expected to come to consensus on about 10 megabytes per second. We are going to have 64 shards just with data only. These shards eventually will have the state execution aspect in a future phase where we can actually run ETH as we know it, Ethereum as we know it, with contracts and whatnot. But that's not to say that phase 1 is not entirely just for fun or just has some uses for it. So some use cases might be having a zero knowledge rollup of transactions, or even a zero knowledge rollup of rollups, kind of batching transactions on there. This paradigm works great for any application you can imagine that's write once, read many times, like a Twitter or a GPG key server, or just like web hosting in general. Could also be a nice like backup data layer for enterprise blockchains. In general, really anything small. This would be good use in phase 0, small amounts of data. Between phase 1 and phase 2, we sort of injected this new state or new phase, called phase 1.5 or 1.5 or whatever you want to call it. And the idea there is that we want to merge these two blockchains that we're running separately. ETH1 and ETH2 are sort of running in parallel. We want to merge them together as quickly as we can. So instead of waiting till phase 2, which is another kind of big upgrade, let's get these things merged faster. So until phase 1, Ethereum today on mainnet is still going to be the proof of work blockchain, and transactions will be processed by miners. But in phase 1 and 1.5, Ethereum becomes a shard of ETH2, and now it's the validators that are processing the transactions instead of the proof of work miners. This upgrade or migration or merging event, it's supposed to be very seamless. So dApp developers or users should not really feel any large pain. By that I mean you don't have to rewrite your contracts or migrate anything. The virtual machine that you know now will continue to operate as it does, just instead of being being secured by proof of work, is secured by proof of stake. All right, and then phase 2, this is the final big piece of the phase rollout for E2. It brings in the state execution. So actually bringing the computer part to the decentralized world computer. Up until this point, we had everything else. We had the motherboard and the hard drives and the power and all this stuff. But now let's do something meaningful with this data. We're going to, the plan is to at least to take the existing Ethereum virtual machine and replace it with a WebAssembly based virtual machine with some minor tweaks to it that are specific to Ethereum. So we call it EWASM. The idea with this is that instead of only having Solidity as your smart contract language, you could use some existing or more mature language that is able to compile to WebAssembly. So basically anything that is supported by the LLVM compiler, which is a lot of languages like Java, C++, and all these other ones. So that'll be nice for developer experience. We'll also have cross-shard transactions are part of the scope here. So even though that your contract may be in shard 5, you can still interact with the contract in shard 6. And further that example, if shard 5, which has its own gas market, each shard has its own gas market. If the gas fees are too high in shard 5, you're able to move your contract to a different shard, maybe shard 6, and put a redirect in that previous place. So anyone who was interacting with your contract now just interacts with it as a cross-contract call. This is in general what I think E2 becomes most useful to the average developer, average user. This has been in research and design. It did start some prototyping and development in early 2020, but it's being built. That's to say, it's being built in parallel with the other phases. It hasn't been launched yet, obviously, because nothing's been launched yet, but it's getting close. So the timeline for phase 2, we're thinking sometime late 2021, maybe into 2022, following phase 1 and phase 1.5. So how are we building this? How does someone get a group of people all across the world, many who have never met or in person, to redesign such a system and rebuild it from the ground up? It starts at the research level. So the Ethereum Foundation has a dedicated research team led by Vitalik himself and a few other really smart guys and girls. They come through with ideas, and then they talk about it either on their forums, which is ETH Research, in person, or various online channels. Telegram and Discord are pretty popular. Then they propose changes in an open source Ethereum 2 specification. This is on GitHub. Then these spec changes are reviewed by everyone, by other researchers, other implementers. Then once we've come to a semi-stable state, we tag a new version of the spec, and then implementation teams implement it and come back with feedback. Typical cycle is to run the features through on GitHub and have it reviewed by the team. In our specific team, our client Prysm, we usually start with a document that's outlining the whole design. We then try to break that up into smaller pieces, put that into a tracking issue on GitHub so that everyone can see sort of the progress of a feature. Then it's implemented, it goes through pull requests, code review, a lot of people on the team involved in code review. Then we do a lot of testing, continuous testing through canary analysis and unit tests and all this integration testing. And then every week or so, we create a new release with the most recent changes from the spec and just in general with feature improvements. Now, let's talk about running a validator and perhaps why you should run one. This is not investment advice. I think running a validator is fun, but you could lose some or all of your money. So just don't take this as like do it kind of thing, but look at it, consider it for yourself if it's right for you, for your risk tolerance. Check it out. There's it's pretty exciting, but at the same time, like I can't tell you that it's foolproof. It has risk. So important thing to understand is how the Prysm client is designed. We use like a server client architecture where you have a beacon node, which is running all of the hard work, doing all the heavy lifting in phase 0. And then you have your validator attached to that. Now, the validator doesn't talk directly to the network, only the beacon node does, but the validator can run multiple keys. So it's not just, in terms of your computational resources, the amount of hardware you need is the same for 10 validators as it is for 100 or maybe 1,000. We've run as many as 300,000 on one laptop. So you should have no problem running multiple on your machine. It's important to consider. Looking at the same table we saw before, but in graph form, you can see that the issuance for the network does increase slightly as the total number of validators are introduced, and likewise the annual return rate is diminished. So if you're one of those, first, let's see, we need just under 17,000 to start. So if you're one of those first 17,000 validators, right away you're going to be earning 15% interest or so. As more validators join, it goes down slightly, but in your first year, you would see somewhere between 15 and 10%. Looking at this little image here on the right, if you had put in 32 ETH, which is 1 unit to stake, it costs about $13,000, which is a lot of money, but considerably less than what you'd need in hardware costs for proof of work. Plus, it's a like a refundable deposit. So when you are done participating, you can claim back your deposit. So it's not a cost. It's just like the only problem with that is just opportunity cost. So it's not too bad. And if you don't have $13,000, well, you can participate in a staking pool where you or some friends and or strangers online can pool the funds together and operate together, or one operator will conduct the validator. So there is like kind of a trust there, but it still can make it more possible for anyone to validate. And then looking at these earnings, approximately every month you'll earn $56 at today's prices if you're running one validator, and that's if you're running on your own hardware at home, that you should still have a pretty considerable profit margin there. You don't need expensive hardware to do this. Some people are running with a Raspberry Pi or an old laptop, or even looking on server. If people have bought servers from Craigslist that are really old, like 5 or 10 years old, for a couple $100, and then they're running it off that. And then on an annual basis, $681 at today's prices. And of course, everything is based in ETH. All your earnings are based in ETH. So if the price of ETH went up, then you would naturally be earning more in dollars. But things to consider: the costs are relatively low, and they do not scale linearly with the number of validators in your operator. So, like I said, 10 validators versus 100, it's going to cost you the same in operational costs. It's just that upfront deposit that's kind of hard to get over. it is a long-term commitment. So withdrawals and transfers and all that kind of stuff don't become available until later phases. So you have to be comfortable with putting your collateral there for some unknown amount of time. I can tell you it's going to be in 2 years, but it could be delayed for whatever reason. There's no guarantee. So keep that in mind. Liveness penalties, you have a risk of losing half your balance if you're not participating, if you go offline. But the thing about this is that it takes something like 6 or 7 years of not participating for you to lose half your balance. So if you went away on vacation for a weekend and came back, you found out your computer was off the whole time, you're gonna be fine. You know, you lost money for 3-4 days, but in 3 or 4 days time, you'll be back to where you were, and then you just continue going. So it's not too bad. The only thing with that is that if the whole network is suffering because people are offline, then your penalties will be increased. But that should hopefully never happen in a healthy network. So shouldn't be too much of an issue. The rewards are higher for early adopters, and just keep in mind that staking is not without risk. There are ways you can misconfigure or misuse your software to get slashed. So you kind of have to know what you're doing in the early phase. Even though there will be guides and things kind of helping you along the way, it's still a considerable risk that you could lose half your balance if you're not if you haven't configured it correctly. So if that sounds interesting to you, there are ways to try it out today. We have a test network called Medalla. It's spelled MEDALLA, and our 2 ways to access this is a long URL, medalla.launchpad.ethereum.org, and it has this nice like Rhino guy. You can click that and get involved in the testnet. So there's no money's required to do this. It's they'll give you some test ether from the faucet, or we at Prysmatic Labs can help you with that, and you can run the software for some time just to kind of see what your gains might be like, or what your operational costs might be like. It's a great time to test that with zero monetary risk to see if it's right for you. And then to recap a good bit of this information, Ethereum 2.0, it introduces proof of stake and blockchain sharding. It's an entirely new blockchain. It's not just a hard fork like we've seen with a lot of other upgrades. It actually runs in parallel, and then the two blockchains are merged together. I don't think this has been done before, at least not on this scale, so it's going to be a really cool thing to see. This is a phased rollout. Instead of trying to launch all of this rewrite at once, we're going to do it incrementally in small pieces. This is expected to complete by the end of 2021, but expect that it might be even later due to the unknown unknowns. Phase 0 is ready to test today with Medalla testnet, and it is launching this quarter. I can't tell you exactly when because no one's told me, but it will be soon. The deposit contract is supposed to go out in the next 2 weeks, and we've been told that the genesis time, or the minimum genesis time, will be in 2020. So it is happening, and that's really exciting. We've been working on this for 2.5, 3 years, and I am very excited and also anxious to get it out there. Okay, and that's it. I think I can get questions. Okay.
So thank you again. It's a great talk. So thank you so much. And I think there were a few questions on the chat.
Sure.
Folks were asking earlier on, and well, right now I guess since the audio is working, so please, anyone who has any question.
Could you go over again how that interest system works? Because I was a little interested in that.
Right. So the interest works. It's based on. I don't have the formula off the top of my head, but it's a function of how many validators are active in the system, and then how you participated. So if you voted or were selected to produce a block and completed those activities, then when the state processes a full epoch of blocks, so every 32 blocks, it counts all of those and then increments the balances or decrements the balances of validators based on whether or not they participated. So as the validator registry or size of the validator registry increases, the amount you earn per operation starts to diminish, and that's to keep the issuance of the network from ballooning. Ultimately, I think that we're trying to find the right. It's like a piece of game theory, right? We're trying to find the right incentives to have participation, but not to over incentivize so that we're giving up too much issuance through the network. That increases inflation and ultimately drives down the value of the currency. So that's kind of why there is a diminishing issuance rate for the percentage.
Oh, okay. I think that makes sense.
Yeah, and if I can find it, there's like a 100-page report that came out this year all about the economics of it. So if you're interested in that, I can find it and then send it to you guys through email or something.
Yeah, that would be very nice if you can kindly do that.
Yeah.
Are there any sort of expected throughput and latency once this the new Serenity kind of rolls out, let's say by 2022?
Mm-hmm.
What's the expected kind of, you had that chart as Bitcoin is 10 minutes and Ethereum 14 seconds, and so what would you expect?
So in E2, we're reducing the block times to 12 seconds. So that's a small improvement there. We're expecting that since we'll have 64 shards, and each shard will be on the same caliber as the Ethereum mainnet is today, if not better, plus some overhead for cross-linking. That, with that in mind, we'll have 64 times the amount of throughput. So whatever, if it was 12 transactions per second, it would be something like 75 or more. Oh no, wait, 600, 700 and something, right?
And what is the justification of 64? I mean, how does the number 64 comes? Why not less shard, or why not more shards?
Yeah, it's a good question. So it's just because 64 is a nice multiple of 2, and with that amount, we can ensure that with our current committee sizes, which are I think 128, that we can always cross-link every shard in every epoch. So epoch is 32 slots, and with 128 in a committee, that means they can cross-link twice. That comes out to be 64. Without it, you might have cross-linking taking more than one epoch, which is not very user-friendly.
I see. In more database terms, when you do also do sharding, you also split your data. I mean, each shard works on a different part of the data. Is that kind of exploited here as well too? And if so, then if somebody wants to run a smart contract that hits all these shards, what are the sort of effect of that?
Yeah, so the benefit you get with sharding is that, or at least in the Ethereum space, is that you can co-locate your contracts in the same shard. So things that frequently interact with each other can have experience a lower gas fee market, because essentially the load is distributed over many shards. So if you're running your DApp, and then CryptoKitties or whatever is popular at the time is blowing up, your app is not necessarily suffering from gas fee increases because it's on a different shard. And so, with that in mind, you're able to break up your data into pieces that are isolated in the sense that they really only interact with these few contracts, and so you serve that benefit of having a lower gas market. I believe also that the part of phase 2, what we're looking at is that some shards can have different execution environments. So we may have some shards that operate on a different set of rules. Maybe they're faster for certain purposes or operate differently. So you get a little bit more flexibility. I know that for sure that when ETH1 becomes a shard, it's going to live on those rules using the classic EVM, but other shards will more than likely use the new EVM, which is using the Ethereum WebAssembly and would require, a smart contract rewrite to support this. At least your smart contract like backend has to be rewritten to conform to the new virtual machine.
And so how does for example, is the user needs to kind of now decide that this smart contract is getting too expensive to run here, or it takes too long to run here, and they switch it around the shards? Is that something that needs to be initiated by the user, or is it the platform can adaptively just load balance these shards?
Yeah, so the protocol does not have any automated load balancing. So at this time, it will be on the user. I do see how we could eventually add it after phase 2, but I think the long-term goal for scaling on Ethereum is we'll get the protocol to this nice level where we have 64 times what we had, and then we'll rely more so on layer 2 things, like state channels and whatnot to get that increased benefit, especially when a lot of the things you see are highly transactional things like Uniswap, where you can do all these swaps off chain and then commit it periodically, maybe every epoch or so, where that could be hundreds or thousands of swaps or transactions batched into one. And that's sort of the longer term goal, is sort of offload that state. But there's no automated load balancing at the protocol level at this time.
Well, seems like a lot of interesting opportunity lies ahead in terms of the work of sharding. So interesting. Any other questions? All right. So I think this is it. So thank you so much again once more for the excellent talk and sort of introducing the Serenity and the proof of stake and all the interesting challenges and what to expect in the next few years.
Yeah, of course. Thanks for having me. It's been great talking to you guys, and yeah, try out ETH2 if you like, and we're happy to hear any feedback. You can find me online. I'm on Twitter, Preston_Van Loon, or on Discord. You can find us on Prysmatic Labs website.
Wonderful. Thank you.